Hello, everyone. Thank you for joining us today for the PCI-SIG webinar, The History of PCI IO Technology, 30 Years of PCI-SIG Innovation. We'll get started here in just a moment. Hello, everyone. Thank you again for joining us for the History of PCI IO Technology, 30 Years of PCI-SIG Innovation webinar. We wanted to take a moment to introduce you to today's speaker, Dr. Debendra Das Sharma, Intel Senior Fellow and Co-GM of Memory and I/O Technologies in the Data Platforms and Artificial Intelligence Group at Intel Corporation. Dr. Das Sharma is also a member of the PCI-SIG Board of Directors and chairs Phi Logical. Now, I'll go ahead and pass it over to Debendra to discuss today's agenda.
Greetings. It's an honor and privilege to do this webinar commemorating the 30-year anniversary of PCI-SIG. It has been a very personal journey for me for more than 25 years. Here is the agenda for today. I will go through the technology journey from the original PCI bus through 6 generations of PCI Express. I will go through the rationale for the key decisions, how we have navigated the evolution as well as the revolution in the compute infrastructure over the past 30 years. I'll shed light on how the PCI Express technology has been and will continue to be a key ingredient in the compute platform for decades as we embark on the 7th generation of PCI Express, which was announced last week. PCI-SIG is an open industry consortium with 900 plus member companies worldwide. It has 9 directors in the board who get elected by member companies every year. The current board members are shown here. PCI-SIG was established in 1992. PCI stands for Peripheral Components Interconnect. SIG stands for Special Interest Group. PCI-SIG is responsible for defining the specifications and mechanisms to support the compliance and interoperability of PCI Express technology and was responsible for PCI before that. PCI-SIG drives the technology from the proverbial cradle to grave. This involves defining the specifications. The base specification defines the behavior of software, silicon, and channel components. The form factor specifications, they define the form factor. There are multiple form factors that exist with PCI Express. The compliance and interoperability or interop test specifications define the test criteria derived from the various specifications to ensure that devices meet the specification with clearly defined pass-fail criteria. We also provide the test tools, test fixtures, and test procedures derived from the compliance and interoperability specification. These test the hardware and software to ensure that a part works as intended. With that, there is a clear outcome of a device passing or failing the compliance test. PCI-SIG administers compliance workshops around the year in various parts of the world. These have resulted in a predictable path to design compliance. The tenet of an open slot with backward compatibility is to make sure that a part designed by any member company, say 2 decades back, will still work in any system today. That's a tall order to achieve. Yet, we have been able to accomplish that and ensured a plug and play ecosystem across 900 companies with thousands of distinct parts over the decades. This is not a coincidence. It's the result of this methodical approach that we have so successfully deployed with appropriate improvements in PCI-SIG since the beginning. PCI started in 1992. At that time, the ecosystem was fragmented across multiple competing standards as shown on the picture on the top left. We had the ISA bus from the PC era, which evolved to extended ISA. We also had the proprietary MCA from IBM. We had the Visa bus, and we had a bunch of different proprietary buses back then. PCI consolidated a fragmented industry behind one interconnect. It started with PC and workstations and eventually made its way to other types of systems such as servers. Consolidation to a single open industry standard brings several benefits. We get better customer experience. Most importantly, we unleash innovation in the industry as one needs to focus on the value add of the device that they're doing without having to worry about making that device work across different bus standards for different systems. You also get an ecosystem where the design IP, the validation IP, and the validation infrastructure can be leveraged from an open market. The picture on the top right shows the platform view at that time. We have one or more CPUs on a system bus. Back then, CPUs were single core based. An ASIC, referred to here as the root complex, it connected the CPUs to each other, to the memory, and to the peripheral devices. In this example, we have 3 PCI buses from the root complex. One of the PCI buses spawns off to multiple PCI buses through a PCI bridge, which means that PCI is hierarchical. So you can go hierarchically and create yet another bridge and then expand to more PCI buses and so on and so forth. The establishment of PCI-SIG with the introduction of PCI in 1992 was a historic event. This would evolve to be the ubiquitous interconnect in the compute continuum going forward, as we will see. So what else happened in 1992? Elvis Presley stamp was introduced by the US Postal Service. So they had two choices, and the country wanted to go with the younger looking Elvis Presley in the stamp. 25th Olympic Games was held in Barcelona, Spain. Terminator 2 movie debuts in 1992. What were you doing in 1992? Assuming, of course, you were born. I was in graduate school pursuing my PhD, unaware of PCI at that time. PCI was a bus-based architecture. It started off as 32 bits at 33 megahertz and 66 megahertz in 1992. In 95, PCI 2.1 was introduced. In 99, PCI-X was introduced with 133 megahertz frequency, which doubled and quadrupled in 2003 in a backward compatible manner. PCI was a layered architecture. The physical layer dealt with electrical and bus arbitration. The transaction layer dealt with transaction flows. And we introduced several new concepts in PCI, which were revolutionary back then. The producer-consumer ordering model established the contract with software on the architectural data consistency model. This model is still valid to date. The mechanism for device discovery, addressing based on a programmable register called bus address register or bar for short, the interrupt mechanism for notifications. These are all new concepts that are still in use today with several enhancements, of course. Now, this goes to show how the concepts introduced through PCI-SIG stands the test of time. The mechanical form factor defined the card volumetrics and mechanical aspects. We saw 3 example slots in this picture on the bottom left. These are the 3 slots on a motherboard, and it shows that you can plug in up to 3 PCI cards in this platform. At a personal level, I started working on PCI 2.1 in 96 when I co-led HP, now HP is the IO transition from its proprietary bus to PCI, starting with their Superdome servers. Since then, I have been working on PCI and PCI Express and enjoyed the journey so far. Now, while buses are simple, they have scaling challenges. Buses are pin inefficient. They also have performance implications with multiple devices sharing a bus. That was becoming more and more apparent at the beginning of the millennium. As a result of this continued IO bandwidth and IO connectivity demand, PCI bus was becoming untenable. So to solve this problem, we introduced PCI Express, a link-based interconnect. It was differential, it had full duplex signaling. We debuted with 2.5 gig in 2003. We supported multiple widths by one, which means that you got a single lane from going from device A to device B and a single lane from B to A back. This is symmetric link. We also have by 2, by 4, by 8, and by 16. Even though we had defined by 12 and by 32, these never took off and were eventually removed. Now, we all know that SerDes links do not interoperate with buses at a hardware level. So the question is, how did we move an ecosystem without that backward compatibility? Well, we embarked on two approaches. We made sure that PCI Express was compatible with PCI from a software point of view. So you could use the old OS, the old drivers, and things would just work, even on a PCI Express based system. The second approach was we also defined PCI Express to a PCI bridge, and the industry developed bridge chips. So you could put a bridge chip on the front end of existing PCI cards so that they can be migrated to PCI Express slots without adding the bridge chip. And that was a stopgap arrangement. Eventually, those cards natively moved to PCI Express, but that enabled us to basically go through that transition. Now, the platform view at that time is shown on the right. The CPUs were still predominantly single core. They were connected through a front side bus to a memory and IO controller chip as shown there. And that chip connected to memory and had PCI Express for IO connectivity. One can have PCI Express switches for larger fan out to connect to more and more PCI Express devices. And of course, switches can connect to switches in themselves and do more fan out. Now, it's interesting to note that in volume platforms, the IO had moved to differential full duplex signaling ahead of the CPU to CPU, CPU to memory, CPU to IO connectivity, which was still front side bus based. Now to the other world events in 2003. The Human Genome Project is completed with 99% of human genome sequenced to 99.99% accuracy. Tesla company was founded in 2003. Space Shuttle Columbia disaster claimed the life of 5 astronauts on board, and it was the International Year of Freshwater. PCI Express is a layered architecture. It's a load store architecture like PCI. And what that means is accesses occur by addressing system memory space. So in other words, devices directly do a DMA, what is known as DMA, direct memory access to the system memory. Similarly, their memory space within the devices is mapped into the system memory space. So it's all, most of them is memory mapped accesses. Now, each layer in PCI Express offers a distinct and well-defined functionality. This allows each layer to evolve independently from a specification as well as an implementation point of view. A well-architected mechanism defines a consistent interface between software and hardware for essential system functions. We have defined mechanisms for discovery of devices. We have device driver association with a device. We do power management through software mechanisms. And these ensure basically seamless interoperability across multiple platforms and multiple operating systems. So, your device can go through multiple platforms, multiple operating systems. You don't have to worry about it as long as you have the right device driver with the right interface defined there. We also define advanced error detection, recovery, and reporting mechanisms in addition to hot plug support to meet the high reliability, availability, and serviceability RAS for short. We had the RAS support for servers and the storage segments, which have high RAS requirements. Now, scalable I/O systems could be built by exploiting the hierarchical architecture using PCI Express switches. So that part gets covered. So that way you can build a large I/O subsystem with lots of PCI Express devices by deploying switches. The transaction layer in PCI Express is a fully packetized split transaction protocol, and it is designed to deliver maximum link efficiency. Packetized protocol means that everything goes as packets, so it's like one entity that you're transferring. Split transaction protocol means that the transactions are, you make a read request, or you make several read requests. You can get the completions completely at a different time. Right? There is no timing correlation between if I send this request at time X, my response, which is a completion, needs to come in time X plus Y. The producer-consumer ordering model, it ensures data consistency, and this provides programmers a consistent model that is independent of the type of I/O device that they're working with. PCI Express technology still uses in-band credit-based flow control mechanism to avoid the added cost of sideband mechanisms while delivering performance at line rate. We defined virtual channel capability for ensuring quality of service support across the hierarchy. So it's possible to have different types of devices to communicate over shared links for power and cost efficiency. So for example, if you're delivering audio, you want to have a guaranteed time-bound bandwidth so that you're not hearing the blips while the audio is playing. Whereas if you're doing storage kind of transfers, those can go in bursts. That's not an issue there. So we define the different virtual channels to carry different traffic types. The data link layer provides reliable data transport services. It's done through a combination of cyclic redundancy check code, or CRC for short. So you send a packet, you do the CRC check. If there is an error, then you ask the sender to resend the packet, which is known as a retry mechanism. We also have defined timeout mechanisms and that's hierarchical in the system in order to ensure better reliability in the entire platform. PCI Express physical layer is responsible for packet framing, scrambling, encoding, decoding, link initialization, everything that's needed at the physical layer. The electrical layer defines the signaling, the circuit behavior, and it accounts for the channel characteristics in order to deliver performance. The mechanical layer defines the form factors. There are multiple form factors supported depending on the compute segment, and those can be evolutionary as well as revolutionary, and we'll see that in the next slide. PCI Express technology has a long track record of being implemented in high volume manufacturing products, satisfying the power efficiency of handheld devices while delivering server grade reliability. So while we have one base specification and require silicon level interoperability across the compute continuum, we support a wide range of form factors. This is expected since different systems have different needs. For example, a smartphone has very different volumetric requirements than, say, a server in a data center. And they have very different power profile. So this slide has some example form factor. things like BGA and M.2 is used on small and thin platforms, where things like CHEM and SFF form factors are prevalent in data centers as well as in your desktop kind of thing. So different form factors for different segments, but all of them make use of the same PCI Express base specification. The same silicon can go across all of them. In the early 2000s, virtualization was being deployed in a big way in clients and servers, which eventually became the mainstay in the cloud segment. Now, this is the time when multiple core CPUs were coming up and having multiple virtual machines, each of which is like an independent operating system, offered better total cost of ownership or TCO as they utilize the hardware resources better. People call them virtual machines, VM for short. Some people also call it system image, SI, they mean the same thing. Now the picture on the right shows how IO was being virtualized. There are two pictures there. The one on the left side, which there are two pictures on the right side. So the picture on the left of that side shows how IO was being virtualized through an intermediary that intercepted all the communication between the PCI device and the different VMs to ensure the isolation across them. So effectively, it was like a software emulation model. So VI stands for the virtualization intermediary that basically intercepts all that communication. PCI-SIG defined IO virtualization for delivering better performance. We define address translation services. We define access control services. That these things, they enable the picture on the right. Here, devices support multiple virtual functions. Each virtual function is assigned to one system image or VM. The root complex implements an IO TLB, IO translation look aside buffer, that does the translation from the SI address or the VM's address space to a physical address space. Only config cycles, which are not performance critical, are emulated through the virtualization intermediary. So those go through the VI as shown in the picture there. However, all the memory accesses are done directly, which results in better performance. IO virtualization has been a critical ingredient in making the cloud computing a reality today. Now let's see how IO virtualization helps IO performance. The graph on the left shows latency, and the graph on the right shows throughput from a study done back then. Now latency is lower with IO virtualization, with native IO virtualization, which is about half, versus the emulated case with an intermediary, and that's that's intuitive. Of course, lower is better here from a latency point of view. And as expected, throughput is better with native IO virtualization, about twice as much. And so this demonstrates the effectiveness of IO virtualization. PCIe 2.0 marks the backwards compatible bandwidth journey. It marks the start of that. Now, the IO bandwidth and connectivity demand needs to keep up with the system performance, which kept moving up with Moore's law. Now, we defined a dynamic speed change mechanism in PCI Express, starting with PCIe 2.0. The link always starts training at 2.5 gigatransfers per second, and all the supported link speeds are advertised during that initial training. So that way, both sides start at the predefined 2.5 gig data rate. And if you're a PCIe 2.0 device supporting 5 gig, you would advertise that 5 gig capability, so that your link partner knows what data rate or data rates you support. And then, since both of you know the capability of each other, then later on you can decide to go to the higher data rate or keep moving the data rate back and forth as the demand is. So these speed transitions happen seamlessly, and this mechanism is still in use today. The promise of backward compatibility is that a Gen 5 by 16 device will interoperate with a by 1 Gen 1 device. The platform view is shown in the picture on the right during PCI 2.0 when PCI 2.0 devices started coming out. Now note that the CPUs in this time these are the volume CPUs, they have integrated memory controller, and the CPUs are connected to each other using differential, full duplex, coherent links that look like PCI Express. And an IO hub was there to provide the IO connectivity. Depending on the platform, you got anywhere between 18 to 36 lanes of PCI Express per socket during this time. So what else was happening in the world in 2007? Well, iPhone debuts in 2007. NASA launches Phoenix Mars lander. Housing bubble bursts, leading to a downturn in the economy worldwide. And there is a devastating earthquake in Peru. The smartphone revolution fundamentally changed the compute landscape that has led to a virtuous cycle of computing that continues unabated to date. Today, PCI Express is the ubiquitous IO across the entire compute continuum, everything from PC, handheld, workstation, cloud, enterprise, HPC, embedded, IoT, automotive, you name it, they use PCI Express. We are really proud that we have one interconnect that serves all the markets. The third generation of PCI Express, in my mind, was a watershed moment. It is that proverbial fork in the road, and you always make the decision you make decides the fate of the, whatever decision you made, right? Now we did the analysis for 10 gig, considering the cost, area, and power constraints. And we found that 10 gig was not feasible at that time for server channels. Server channels were 20 inch long. The material was FR4 on the motherboard, which was the volume material, and you went through two connectors. So that was not possible. So something or the other had to give, either cost, area, power, one of those things had to give. The client channel was 14 inch with one connector. Mobile channels were about 8 inches, one connector. They had no issues. They could go to 10 gig. But the server channels could do 8 gig. They couldn't do 10 gig. So that 8 gig was based on the technology choices available back then. So this represents the fork in the road. The question is, do we go with 8 gig and leave the server behind? Do we go with 10 gig and leave the server behind? Or do we go with 8 gig and not get the doubling of the bandwidth? Neither choices were acceptable. So what we did was we took that 8 gig path, but we developed an innovative solution to deliver the bandwidth or doubling. So it was a two-pronged approach. The data rate we said will be at 8 gig. So that way we are going to take all the segments with us. They will all move with us as PCI Express going to 3.0. But we had a 25% shortfall in the bandwidth because 5 to 8 gig is 1.6x. We got an additional 25% boost in bandwidth by going with a novel 128B, 130B encoding mechanism that we innovated with PCI Express 3.0. So the 128B, 130B encoding gave us 25% boost. So what is 1.25? And then the 5 gig to 8 gig was 1.6. You multiply that 2, you get the 2x bandwidth that we needed. The same 128B, 130B encoding went on to be used for 16 gig and 32 gig data rates also. Now we had several other challenges at 8 gig. Without the DC balance guarantee of 8B, 10B, we had to handle DC wander and crosstalk. So we introduced a new scrambler for statistical relief that is still in use today for subsequent data rates of 16 gig, 32 gig, 64 gig, and I'm pretty confident will be used in 128 gig. We had to come up with a new equalization mechanism to mitigate the channel effects. And that is still in use today for subsequent data rates of 16, 32, 64. And again, I'm pretty confident we'll be using the same mechanism for 128 gig. Now, on hindsight, 8 gig was a very bold move, but one of the best decisions we have made. We stayed true to the one interconnect for all philosophy. We also got relief in subsequent data rates. We doubled from 8 to we doubled when we doubled from 8 versus when we doubled from 10. We basically, our subsequent data rates went to 16 gig, 32 gig, 64 gig, versus us having to go for a much more tougher problem of having to deal with 20 gig, 40 gig, and 80 gig. So one of the best decisions we have made. Now, there are two sets of platform views that are shown in the right. The important thing to note is that due to the demand and widespread adoption of PCI Express, the CPU now has integrated PCI Express. So you'll see that PCI Express coming out of the CPU SoC. This was a huge accomplishment and testament that PCIe was the IO in the platform. Whether it is a scalable platform on the top or a highly integrated platform in the bottom. Also note that the PCIe lane count increases drastically in the platform. Now we are in the hundreds of lanes of PCI Express in a scalable platform per CPU socket. Now to the notable world events in 2010. We had Winter Olympics in Vancouver. Burj Khalifa opens. SpaceX, the Dragon capsule returns back to the Earth. Basically, the first successful private spacecraft endeavor starts at that point. How do you remember 2010? I remember 2010 for the transformation to the compute landscape brought by PCI 3.0. And of course, I was fortunate enough to be a part of that. This slide shows the 128B, 130B encoding on a by 8 link. As you can see, the teal color has 01, which is known as the sync header, followed by 16 symbols or 128 bits. Each symbol is 8 bits or a byte of data. I got 2 bits of sync header, 128 bits of data. So that's hence the term 128B, 130B. Framing tokens like STP, SDP, they mark the start of the packets with their own independent CRC protection to ensure high reliability, but basically those are like the packet markers. And then after that, you got the different types of packets. Now with the handheld devices such as smartphones and tablets gaining popularity, PCI Express had a drawback that needed to be addressed if we were to be relevant in that segment. Our idle power consumption was in milliwatts. This is when you don't have any traffic going on, we still consume milliwatts power. Now, it was pretty good. It was excellent for desktop and server where you had a power source. But if you are in a handheld segment and you're trying to gain a prolonged battery life, we really needed to up our game and go down to microwatts worth of power. So we developed an innovative solution called L1 Substates that enabled us to do exactly that. We consumed single-digit microwatts of power in idle states. We even surprised ourselves, and that mechanism is circled in the table on the right. Fundamentally, what we did was we floated the differential pair versus driving to a common mode voltage. We turned off PLLs. We turned off a bunch of other circuitry like electrical idle detection circuitry. We leveraged the existing very low speed clock rec for doing the wake up. With all of these technical changes, PCI Express found a firm footing in the handheld segment. The combined innovation power of the industry came through to solve a challenging problem. Very simple, very elegant, but very powerful solution that made us really relevant in the handheld segment. Now, as mentioned earlier, server channels were a challenge for 10 gig. So naturally, 16 gig was a step function. And that caused us to navigate that speed transition very carefully. And that resulted in 7 years for this data rate jump. So the question is, how were we meeting the bandwidth demand during this time? As mentioned earlier, it was due to the increased number of lanes. For example, networking cards increased in width from by 4 to by 8 to by 16. The aggregate bandwidth in the platform was delivered through hundreds of lanes, like we talked about. Now, in the meanwhile, low loss materials like Mectron 2, Mectron 4, Mectron 6, they were available in volume. We were doing packaging and connector improvements. These with the low loss materials caused the channel loss to improve significantly to make 16 gig possible. With improved platform volumetrics, a significant number of server platforms stayed within the 12 to 14 inch and one connector. We also introduced retimers. So for short channels, we had no retimers. For longer channels with a riser, as we have shown in the picture on the right, you needed a retimer to extend the channel reach. 16 gig was primarily a speed upgrade. We also made protocol enhancements for performance scaling. Now, a significant shift happened with PCIe 4.0 due to the compelling area, latency, and power characteristics of PCIe 5. It was being adopted for non-PCIe load store applications like symmetric cache coherency protocols in a platform. Now to the other important world events that happened in 2017. Cryptocurrencies, they go mainstream. Bitcoin grows by 20x. The global growth picks up, and we are in the midst, in that time frame, we are in the midst of the longest bull run in history. Britain invokes Article 50, known as Brexit, and something very closer to home, Golden State Warriors win the NBA championship. Now, with cloud computing driving the compute, memory, and I/O demand, we introduced PCIe 5.0 in 2019, 2 years after the introduction of PCIe 4.0 in 2017. 32 gig was primarily a speed increase with channel and component improvements. By now, PCI Express PHY is the ubiquitous PHY in the platform with the best area, latency, power efficiency in the industry, bar none. PCI-SIG formally defines alternate protocol support that enables coherency and memory on PCIe 5. Compute Express Link, a new industry standard, comes to play with PCI Express PHY by adding memory and coherency protocols on top of PCIe protocols to solve a class of data center problems. The picture on the right shows a platform view where PCIe 5 is used for PCI CXL cards connectivity, along with acting as a cache coherent link to construct a symmetric multiprocessing system or SMP system. The huge implication is that PCI Express PHY is now solving the memory bandwidth challenge, as the number of DDR channels, which is still based on bus-based interconnect, it's starting to become very expensive in platforms. We also see the emergence of PCI Express as a rack-level interconnect for resource pooling. This is a new usage model that has a lot of promise to reduce the power and the total cost of ownership in data center. So fundamentally, PCI Express, it stands for Peripheral Component Interconnect. And as you can see, PCIe 5 is not just in the periphery, it has moved right to the center in the platform. So along with the periphery, it is in the center. It's getting out of the box into into the rack through cables and all of that. And its scope has increased tremendously. Again, thanks to the combined effort of the 900 plus member companies and all the innovations that they bring to the table. There is just no other PHY that offers this level of area latency and power efficiency in the industry. So very well deserved place. We again, we are solving, of course, the IO connectivity problem. We are addressing the challenges, but at the same time, we are also helping solve the memory bandwidth challenge, and we are helping solve the CPUs to CPU connectivity problem. We are helping to become the rack level interconnect in the data center to derive better TCO benefits. So it's a great place to be. So what else do we remember 2019 for? There was a fire at the 850-year-old Notre Dame Cathedral in Paris. The first all-woman spacewalk by NASA astronauts happened in 2019. And on a very somber note, towards the end of 2019, COVID-19 strikes with a lot of implications on mankind. The doubling of data rate runs to a major stumbling block with PCI Express 6.0. Now with the area, power, performance, and cost constraints, we could not double the Nyquist frequency to get to 64 gigatransfers per second. Right. So we decided to keep the frequency the same as 32 gig, but we instead did 32 gig was binary encoding, but instead of doing the binary encoding, we decided to deploy the voltage. In other words, we shifted to 4 voltage levels to encode 2 bits. So frequency is the same as 32 gig, the previous data rate, but instead of doing a binary encoding with the voltage, low being 0, high being 1, for example, now we have 4 voltage levels. So as a result, it's known as PAM4 signaling, which stands for pulse amplitude modulation, 4 levels. This is shown on the picture in the top right. You can see there are 3 eyes representing the 4 voltage levels in order to encode 2 bits. Now, while keeping the same frequency as the prior data rate of 32 gig helps the channel reach the power, it significantly increases the bit errors as the error susceptibility increases dramatically because we have squeezed the eyes so much. And we model the errors and the correlation, which is shown on the picture on the bottom right. Now, to get around these errors, we needed to deploy forward error correction or FEC, and that has the drawback of added latency. As we always do in PCI-SIG, before we start solving or start doing a lot of work, we put together the guardrails. So that way we ensure that we meet those guardrails. It's in a table format, and the table here represents those guardrails. So I will go through that. So metrics, so you'll see that there are 2 columns, metrics and the requirements, clearly specified requirements. So the data rate 64 gig will go with PAM4 because of what we just talked about. And as I said, with FEC, we are going to get added latency. The question is, how much of added latency is acceptable? Well, ideally, it should be 0 nanosecond of latency adder. And we actually get very close to that. But we said that from a requirement point of view, it needs to be single-digit nanosecond for transmitter plus receiver, including the forward error correction for PCIe. And the note there is that networking standards have done PAM4 and they have deployed FEC, but in the process they have paid 100 plus nanoseconds of additional latency because of the FEC. We in the load store world simply could not afford that. So especially if you're doing memory accesses, there are applications where even a single nanosecond will have noticeable performance impact. So that's the requirement. Bandwidth inefficiency, in other words, how much of because you are going to have additional FEC and all of that, you're going to eat into the bandwidth efficiency. But we said that bandwidth inefficiency should be less than 2% over what we got in 32 gigs. So in other words, if you had an application and you are getting bandwidth X at 32 gig, when you went to 64 gig, you should get no less than 1.98x. Assuming, of course, you can consume all that bandwidth. Reliability is measured in FIT, or failure in time, which is the number of failures in a billion hours. So we said that our FIT, or failure in time, needs to be significantly less than 1 for a by 16, very close to 0. Channel reach should be similar to PCI 5.0. And we also still have the retimers, maximum of 2 retimers. And power efficiency should be better than 32 gig. Ideally, we want it to be half, but in general, after a couple of design cycles, people tend to go and hit that number. So we'll start with not quite the half, but at least some reasonable number, which is less than 32 gig, and then we'll hit the power profile that we are after. And in addition to that, we also introduced this notion of L0P so that we can have power that is proportionate to the bandwidth consumed. So very aggressive low power entry exit requirement. And in general, we need to be high volume manufacturing ready. We need to be cost effective, scale to hundreds of lanes in a platform, and of course be fully backward compatible. So PAM4 is not new to the industry, but the latency constraints required us to develop very unique and innovative solutions. And this is none of these requirements were negotiable, so to speak. So we're still not past the month of June in 2022. We still have a couple of days remaining, but what else has happened so far in 2022? Well, Golden State Warriors win the NBA championship. And PCI-SIG last week celebrated its 30-year anniversary in person on June 21st as the ravages of the COVID-19 pandemic subsides. So very excited to see a lot of people there. So it was a great experience, especially being in the room with several people that have since retired, and they all got together to celebrate the 30-year anniversary of PCI-SIG. Now, there is a separate webinar that I have done, which delves a lot into the details of PCI 6.0. I have put a reference to that at the bottom right corner. So you can go and watch that and know a lot of details about PCI 6.0. I'm just going to talk about that in very briefly here. PCI Express 6.0 makes a significant change to the encoding with the introduction of FLITs. FLIT stands for Flow Control Unit, which is 256 bytes for PCI Express 6.0. Now we correct most of the errors through a lightweight FEC and use the link level retry to correct the rest. The raw first bit error rate is 10 to the power minus 6. We deploy gray code and pre-coding. We constrain the DFE tabs in order to minimize the burst error on a given lane. The retry probability versus that FBER graph is shown in the slide here. It illustrates the trade-offs. So what it demonstrates is that for a raw burst error probability of 10 to the power minus 6 or better, the single symbol correct FEC that we have done for PCI 6.0 is desirable to meet the performance and reliability metrics. So we saw that this results in a retry probability of 5 times 10 to the power minus 6 in the table on the bottom left. It results in a bandwidth loss that is significantly less than 1%, which is acceptable. And it doesn't have any measurable impact on the application level. And the FEC latency that we have measured is less than 2 nanoseconds for a by 16. So great outcome there. Now the FLIT layout is shown in the far right for a by 8. 256 byte FLIT consists of 236 bytes of transaction layer payload, 6 bytes for the data link layer payload, 8 bytes of CRC, which offers very robust detection. And as you can see by the fit, which is very close to 0 in the table, it's 4 times 10 to the power minus 7, which is as close to 0 as you can get. And we deploy a 3-way interleaved FEC as shown by the 3 sets of colors. And that results in a FEC of 6 bytes because for each color it is 2 bytes of FEC. So that results in very low latency. Now the resulting bandwidth efficiency is shown in the graph on the middle at the bottom. Now it shows that in most cases you will get greater than 2x bandwidth because of the lower overhead of the flit mode. Basically, since we removed a lot of the packetization overhead, we gain back, in fact, in terms of the bandwidth efficiency. Our power is low, latency is almost flat. Basically, PCI Express 6.0 involved significant innovations for a load store IO to sidestep the latency impact that other standards have paid with PAM4 signaling. This was critical for memory accesses with PCIe as well as other coherency and memory protocols that run on PCIe 5, where even a single nanosecond of latency adder can have noticeable performance impact. So in conclusion, 6 generations of doubling the bandwidth with backward compatibility with PCI Express, it's an impressive feat, right? All along we have kept the latency flat. Power efficiency has improved generationally. In my mind, when I started, I thought 3 generations and a decade would be success. So clearly we have far exceeded that success criteria in a good way. And what's important is that we saw no signs of slowing down, and PCI-SIG has the expertise and the track record to continue to deliver. PCI 7.0 specification work has started. We are going to go to 128 gig PAM4 and use the same encoding as 64 gigatransfers per second. We need to look into protocol enhancements to continue to deliver the performance. We need to comprehend a fabric style multi-ported connectivity with high bisection bandwidth to deliver better performance and resource utilization across nodes. So fascinating journey. The journey continues. Consider joining PCI-SIG if you have not done so. I'm looking forward to the next few decades of these exciting innovations to continue. And let's see if there are any questions at this point.
Great. Thank you so much, Debendra, for sharing your expertise. We'll now take some time to answer some questions from the audience. And just a reminder, if you have any questions, please enter them in the chat now. Okay, so the first question we have here, is there technology that allows the root complex to hot plug and the devices to remain active?
So hot plug applies to the devices, and it basically says that when can you remove a particular device safely, and then plug some other device back and things of that nature. I think in this case, the question is that can we remove the root complex and still have the devices active? Well, today a device is connected to one root complex, so you cannot really remove that hot plug that root complex, and the device will remain active, right? The device will basically, it's effective. That device also gets hot plugged out along with the root complex. Now, I did briefly mention about multi-ported and all of those things. If you did that, and which is one of the things that we should be looking at, in that context, you can, of course, at that point, if that is the case, then you can hot plug the root complex and the device can still be active because it still needs another path to another root complex.
Great. So our next question is regarding the PAM4 performance. Is there any study to show what PCB laminates material used to manufacture the PCB help achieve the metric or requirements from foil 20? If not specific supplier names, do you know the main electrical characteristics such material should have?
Yeah, so we specify things in terms of the channel loss, in terms of dB per inch, and of course, as the question says, I cannot go through specific supplier names. You can, of course, look them up, but we do have, a loss characteristics that we specify, and we go through those in a lot of details. And yes, one of the metrics that we use is the channel loss in terms of dB per inch for a given Nyquist frequency.
Great. Our next question here, what is the key feature to support PCIe 6.0 less than 10 nanoseconds latency, and how do they work?
I would refer you to the webinar that I had done, but the key feature for PCI is a few things that happen with less than 10 nanosecond of latency adder, right? Which is in most of the cases, the latency is basically flat from PCI 5.0. And the thing is that, sure, when you decode the flit, you have to accumulate for the flit, and you have to decode if the flit has any error, check for the CRC, and then only you can accept that particular flit. That FEC latency, because of the way we have designed the FEC, is it does add, one or 2 nanoseconds worth of latency, but we do save in terms of things like sync header aggregation and all the packetization, depacketization that the physical layer did. All of those overheads we saved on. So and then of course running at 64 gig, you tend to run you accumulate things a lot faster. So in that particular webinar, I go through the case by case basis in terms of what the latency impact is. So that those are the tricks that are techniques that we have done. CRC, for example, even though we have a very strong CRC is it's 8 to 10 levels of logic, so it doesn't add much to that latency, right? So we have made all the right trade-offs, and the other thing that we have done is that we have made sure that the round trip in terms of the acknowledge and everything else happens in a predetermined time, and that helps a lot.
Great. So the next question is regarding the PCIe 7.0 specification, which was just recently announced. When can we expect a basic version of the specification?
So our specification development goes through things like 0.3, 0.5, 0.7, 0.9 before the final specification goes out. And we said, by 2025, we should be done with PCI 7.0. So consistent with that, the intermediate versions of the specs will come out. And beyond that, I'm not going to say much about when those sub 0.3, 0.5 and others will come out. If you are, of course, a member of PCI-SIG, you are going to get those. And if you are in the work groups, you are going to be participating actively and helping develop those.
Great. So the next question here, can we connect downstream port of one switch port with a downstream port of another switch port or another switch?
One switch to another. Yeah, so that particular question has to do with something that is known as non-transparent bridges. People do that today. It's we define it as some people call it a host-to-host link. Some people call it a non-transparent bridge. So people do that, especially for applications like storage, where you want to replicate data and things of that nature. And I've seen that being deployed since the beginning of PCI Express. So and by the way, it's not just downstream port of a switch; it's also a downstream port of a root complex directly connected to the downstream port of another root complex, and that has been a mainstream, not a mainstream, but in the storage segment it has been quite mainstream for quite a while.
Great, thank you. So that is actually the last question I think we have time for today. So we just wanted to thank everyone for attending today's webinar. So the slides for this webinar will be available to download on the PCI-SIG website. And we did have a few questions about a recording, and yes, a recording for on-demand viewing will be available both here on Bright Talk and also on the PCI-SIG YouTube channel. Any questions we didn't get to today will be answered in a future blog. So look out for that, and wanted to say thank you again to Debendra for presenting and to everyone who attended today.
Thank you all. Bye.